All right, so this is Math 146. We're in section 7.1. We're going to be talking about sequences. And the simplest and probably easiest definition for sequences, especially mathematically, what we're going to be talking about is a sequence is a list. That is simply what it is. It is a list. Now, usually the list is in some kind of determined order, some kind of a specific order. And since we're talking about this in math, we're going to be talking about some kind of a mathematical specific order. Um, so something very simple, like if you saw 1, 1/2, 1/3, 1/4, and the three little dots there, I think are actually called ellipses or something like that, kind of like an ellipse, but it's like or ellipses, I think is, I don't know. I call it dot, dot, dot. It's just easier for me. But I think there's an actual technical term to it. But in any case, that just means that the sequence or the list of those terms is going to keep going following some kind of a pattern. And hopefully you can see that we do have a pattern developing there. I've got 1, 1/2, 1/3, 1/4. You would expect the next one to be 1/5 and then 1/6 and so on. Basically, your denominator is going up by 1 while the numerator is holding steady. And that's generally what a sequence does. It's going to follow some kind of a defined pattern. And again, it's just a list of those terms. So let's go through a couple of the things that we need to know. First of all, this one right here, because it is literally the first term, is considered the first term, but we have a notation for that, and we list all of the terms as being a values, and because this is the first term, it is a sub 1. Likewise, this one here, because it is the second term, would be a sub 2, a sub 3, a sub 4, and eventually you're going to go off to a specific term that will be able to define any term of your sequence, assuming that it can be defined this way. And this one would simply be 1 over n, where n is going to represent a specific whole number value that you would be plugging in. So this would be your nth term. And that would define any term in the sequence. So, for example, if I want to find the 78th term of the sequence, I would simply plug in 78 for n, and that would be 1 over 78 in this specific case. Now, the subscript that you have will not always match a specific number, like in this case, the denominator happens to be that same number. That will not always be the case, but it does kind of help to be able to see what we're doing. And we call the actual sequence that we're talking about here a set of values, a sub n, where again, this follows some kind of a pattern. And in this case, the sequence of values would simply be 1 over n. And if you couldn't quite see how to figure out that 1 over n part, that is something that we will eventually be talking about on how to look at. But again, basically this thing right here, this a sub n, is what is known as the general term. General term. And it's the one that will allow you to find any term of that specific sequence. So again, let's just go back real quick. The sequence, in its very, very easiest definition to think about, is a list in some kind of defined or specific order. All right, so let's talk about, given a general term, how we would find this first so many terms of a sequence, because if they keep going on forever, you can't necessarily find all of them, but we'll talk about that because that's something that's slightly different later on. So let's do an example where our a sub n, your general term of the sequence, is defined to be n minus 1 divided by n. Excuse me. And all I'm going to ask you to do here in this specific case is to find the first 6 terms of the sequence. Now keep in mind that we count, you don't start counting somebody with a negative number. You say, oh, you're the negative second person in line. You're the negative first person. You're the 0th person in line. We don't count that way. Um, there are times where you have subscripts of a 0, but that's something a little bit different that goes into some other portions of things. When we're talking about sequence or lists, you count just like you would normally count. If you saw a whole bunch of people in the room, you would say, okay, 1, 2, 3, 4, 5, and so on, and you would just start counting the people. So you always start counting with a 1, and the numbers, the subscripts will always be whole numbers because of the fact that again, we don't count, you don't go around the room, you're number 1, you're number 2, you're the 2.2 person here, and then you're the 3.5 person. It doesn't work like that. You count in whole numbers, so we can, all the subscripts will be whole numbers. So in this case, if I wanted to simply list the first 6 terms, I would just say, okay, a sub 1. Well, what you should notice is the 1 here takes the place of the n here, so that's exactly what it does in the general term here. You simply plug in 1 and you simplify. That's 0 over 1, which of course is 0. So then we'll go with a sub 2. Substituting a 2 in for n, you would get 2 minus 1 on top, which is 1 over 2, or 1/2. A sub 3. Plugging in a 3, you're going to get 3 minus 1, which is 2, over 3, so we get 2/3. And I'm sure you can probably pick this up pretty quickly. A sub 4, 5, a sub 6, because I did ask for the first 6 of them. So plugging in a 4, you're going to get 3 over 4. Plugging in a 5, we'll get 4 over 5. Plugging in a 6, we'll get 5 over 6. And again, I think you'll probably be able to start picking out patterns, which is good because when you're not given the general term and you are given instead the actual just list of the terms like a sub 1, 2, 3, 4, and 5, you might have to come up with that general term, and we are going to do an example of that later. Okay, so now let's do one where it's got something that happens that's just a little bit different. Hopefully you'll be able to see this pretty quickly. So in this case, and the fact that I use a B as opposed to an A doesn't really matter. I could use a P sub n or a L sub n. It doesn't really make any difference. It's just another sequence. This one is going to have a -1 raised to the n plus 1 power, and then times 2 over n. That is going to define our sequence. So once again, we want to find the first 6 terms of this sequence. So we're going to go, oops, not A, getting to have it B sub 1, B sub 2, B sub 3, 4, 5, and 6. And now let's see what we get. So if I plug in 1, first thing I have to deal with is the fact that I've got that exponent there. So I've got -1 to the, now it will be the 1 plus 1 power, which is 2. So it's -1 squared. Well, that makes the -1 positive. So then I still have to plug in 1 to the 2 over n part, which is going to give me 2 over 1, so that's 2. So I get a +1 times 2, which is +2. If I plug the 2 in, now if I plug the 2 in right here, that's going to give me a third power. Well, -1 to an odd power is going to keep it -1. Then I got to plug the 2 in to the 2 over n part, and that's going to give me 1. So I'm going to have a -1 times 1, so that's -1. And then if I plug in 3, well, now that's going to give me an even power for the -1, so it'll make it a +1. And then I'm going to get a 2 over 3, so it'll be a +2 over 3. Plugging in 4 gives me an odd power, making it negative. So that'll give me a -2 over 4, which is a -1/2. Plugging in 5 gives me an even power, so it's positive, so we get 2/5. Plugging in 6 is an odd power, which is negative, so we get 2/6, which is 1/3, but it's negative. So what you can see there, and this is probably the most important part, because plugging in the numbers into the 2 over n part is easy and simplifying. This piece right here, when you have a -1 raised to either an n power or an n plus 1 or an n minus 1 or something similar to that, is basically what is called an alternating term. What that's going to do is it's going to alternate your your terms by sign. So you'll have a positive, a negative, a positive, a negative, or it could start off with a negative and a positive, depending on how the exponent is defined. So we have that alternating term, and that's really important to see that. So when you have that -1 raised to a power of either n, n plus 1, n minus 1, or something where the powers can change between odd and even, then you will have an alternating term. All right, let's take a look at another example, which is written just slightly different, which is what makes it interesting. So here we're going to have a C sub n, which is defined as a piecewise. So it's going to be n if n is even. And then it's going to be 1 over n if n is odd. So that's how our sequence is going to be defined. So again, we're going to write out the first 6 terms. So we're going to have C sub 1, 2, 3, 4, 5, 6. And this is actually a really simple one, but it's just something, again, it's just written in a slightly different notation because of the fact that it's written as kind of a piecewise here. So again, if n is even, it's just going to be the n value. If n is odd, then it's going to be 1 over the n value. So when I go to C sub 1, the n value is 1, which is odd, so it's going to be 1 over 1, which of course is just 1. Then if I go to 2, 2 is an even number, so it's literally just going to be that n value. So the second term is 2. 3 is odd, so now that'll be 1 over the n value, so it'll be 1 over 3. 4 is even, so that'll just be itself, 4. 5 is odd, so then that'll be 1/5. Make that look like a 5. And then 6 is even, so that would be just 6, and then that pattern would keep on going. Again, something just slightly different, just a different way of seeing it. All right, so now let's go the other direction. We're actually going to take a few of these things and look at the patterns, because seeing the patterns of these numbers is going to be really important as far as developing what the sequence could look like or its general term. And basically what you have to be decent at is functions. You've got to be good at recognizing something which is linear and why it's linear. You have to be good at recognizing something which is exponential and what makes it exponential, or something maybe which is a like a quadratic term or a cubic term or something like that. And that's what we're going to work on with this one in particular. So let's do a few of those examples. All right, so our first one here, we'll call this letter A. We're going to be given the sequence, which is written as e squared over 2, e cubed over 3, e to the 4th over 4, and then dot, 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 and so on. So again, what our job to do is to figure out what the general term is. Now, I like to approach this in a very specific manner. I look at 3 things. I look at what the pattern, if there's a fraction, by the way, this is fraction. I look at the pattern in the numerator, see if I can figure out what the pattern is there. I look at the pattern in the denominator, see if I can figure out what the pattern is there. And then I look to see whether we have some kind of an alternating term, meaning the signs are going to switch back and forth. Those are the 3 things that I really look for. Now, there can be other things that come up, but those are at least the first 3 things that I'm going to look for, because it's generally what's going to help. So the first thing I'm going to do is I'm going to take a look at the pattern of the numerator. Well, you can tell that there's an e every single time. So that's there. You just have to know that, okay, so the exponent of the e is changing. And while it's not written there in that first term, the exponent is a 1. So you can see that the pattern goes 1, 2, 3, 4. Well, that's just following the number of the term, because this is your a sub 1, a sub 2, a sub 3, a sub 4. So you can see that the exponent is the n value. So we're just going to put an n up there, because that's how the pattern is developed. And then again, technically that first term is e over 1. So you can also see that the denominators are following the pattern 1, 2, 3, 4. That is linear. Okay, it's increasing by 1 every single time, so it follows the pattern of a line, where the slope would be 1, or the rate of change, or whatever you want to call it, would be 1. But in this case, it's even easier to see. Again, that is just literally the n value. You should be able to see that the n value is the same as the denominator, so that would be divided by n. And that would represent your general term. So your a sub n term here would be e to the n over n. All right, let's try another one. So this time it's going to be 1, 1/3, 1/9, 1/27, and so on. So again, we're trying to come up with the general term. Well, in this case, the numerator is really simple. It's just 1. There's nothing else going on there. But the denominator is changing. So the denominator is going from a 1 to a 3 to a 9 to a 27. So basically what you need to recognize is that those are powers of 3. And you might say, well, how is 1 a power of 3? Remember that any number raised to the 0 power, other than 0, is going to be 1. So it is technically a power of 3. But then you might say, well, wait a minute. This is the first term. How do I get a 0 there? Well, that's a great question. Because this is the second term, here's the third term, here is the fourth term, and so on. And you might say, well, I can't take 3 and raise it to the n power, because if I plug in a 2, that should give me 9, but that's here, not there. So we know that that's not going to be raised to the n power. But again, remember, what I need is for this thing to be raised to the 0 power in order for me to get a 1 in the denominator. This one has to be raised to the first power in order for me to get a 3 in the denominator. This one has to be raised to the second power. So what you should be able to see is I'm taking all of these n values, and we have to subtract 1 to get there. Now, if you were to plug in any n value, it should follow your pattern. For example, if I were to plug in 4 right here, I would then get 3 to the third power, which is the 27 in that denominator. So that is what's going to work. So again, this is just starting to see and develop patterns and be able to notice what it is that you need to do. So that becomes your a sub n term, 1 over 3 to the n minus 1. Let's make that look like a 3. There we go. And that is your general term. Okay, let's do another one. So this one is going to be a very simple one to see. 1, 3, 5, 7, and so on. What you should see is that each one of these terms is increasing by 2, right? 1 to 3 to 5 to 7. The next one will be 9, 11, and so on. You should be able to tell that it's going up by 2 every time. That one's not too difficult to figure out. So if it's increasing by exactly the same amount every time, so it would be adding 2 every time, again, that is a linear pattern. So that basically says, okay, so I'm going to have some kind of linear function, like a y equals mx plus b. So you're thinking mx plus b, but we're going to put it with n instead. So we can even write that here, mx plus b. We know that the slope is 2 because that's how it's changing. X is like your variable. But we have to figure out what the b is. Remember, this is a sub 1. If I were to simply plug in 1 into my n right now, I would get 2. I would not get 1. But I can fix that easily by subtracting 1. Now, if I were to plug in 1 for n, I get 2 minus 1, which is 1. If you plug in 2 for n, you would get 4 minus 1, which is 3, and that's the second term. So there we go. So your a sub n here is linear. It's 2n minus 1. Again, that's probably the easiest way to see it. And linear ones are going to be some of the easier ones, I think, to pick out. I won't guarantee it for everybody. Some people see geometric or exponential easier. Some people see other patterns easier. Just linear should be one of the easier ones. All right, and then we'll go with 1, 4, 9, 16, 25, and so on. And hopefully everybody can recognize that those are simply squares. Those are perfect squares. So simply you're going to have n squared as your general term. There's no extra things to this. That is literally just what it is, because 1 squared is 1, 2 squared is 4, and so on. So a sub n here is n squared, and then we'll do one more. And by no means, like I said, is this everything. This is just the start for us. All right, and there we have a pattern. Now we're back to a fraction. Once again, we're going to look at three parts. We're going to look at the numerator, we're going to look at the denominator, and in this case, we do seem to have that alternating term because every other term is positive and negative. So that's going to be a part of it. Because I see that, I'm going to write in a -1 to some power. I just have to figure out how to write the power. We'll come back to that at the end. The numerator is just 1 all the time. And then the denominator looks like it is following the pattern of n because it's going to be 1, 2, 3, 4, and so on. So that's going to be n. Now we just have to determine what the exponent for the -1 is going to be. And since I need that first term to be positive, if I were to simply say it follows n, that would not work because n would be 1 for the first term, which would make it a -1. So we can either do one of two things. We can either subtract 1 or we can add 1 to n. Doesn't really make any difference in this case. So you can either subtract or add 1. Either way, you're going to start off with that positive value, then it'll alternate back and forth. So your a sub n term here is going to be -1 to the n minus 1, oops, come on now, times 1 over n. That is supposed to be a times. I'm not doing that very well. We'll just do it like that. There we go. All right, so that is how you kind of develop the pattern here. We're going to talk about a couple of more topics, and then we're going to come back with a second video, which is going to show us summation notation, because we're going to need to know that and how to find some sums of these sequences. This might be something which you have seen, which you haven't seen. I'm just not sure where this is at in most curriculums. We are going to talk about something which is called a factorial. If you have taken statistics, you have probably seen this, or probability of some kind. You've probably seen this already. A factorial looks like this. It's the exclamation point. That is literally the way the factorial is written in mathematics. It's the exclamation point. So that is read n factorial. And a factorial is defined to be whatever the n value is your starting point, then you multiply by every whole number all the way down to 1. For example, if I were to have 7 factorial, the definition is 7 times 6 times 5 times 4 times 3 times 2 times 1. That is literally the definition of a factorial. Factorials are only defined for whole numbers, so you can't have a 7.2 factorial. That doesn't exist. You can't have a -5 factorial. Again, not a whole number, that's an integer. Whole numbers, if you're not familiar, are 0, 1, 2, 3, and so on. So basically it starts at 0, and then it's all of your counting numbers starting with 1. Those are whole numbers. And so you might actually have already thought of this. 1 factorial is an easy one because it is just itself 1. But I did say it was defined for all whole numbers, which includes 0 factorial. Now, while there is a really interesting proof to this, and it's pretty cool if you look it up, and there's a whole bunch of different ways that I've seen people prove this, for now, I think it's going to be just good enough to accept that 0 factorial is defined to be 1. Okay, so that is the definition of 0 factorial. And that does come into play, so we just need to know that. If you're really interested as to why that is, again, go ahead and Google or look up on YouTube or something like that what the actual proof for 0 factorial is. It's pretty interesting. We are going to be much more interested in doing this for general terms, something like n factorial. Well, remember, because we're dealing with sequences, n is a whole number, so it works. N factorial would be defined to be starting with n and then multiplying that by every possible whole number all the way down to 1. Well, the problem is, of course, we don't know where n starts, and we don't know what n is, but we do know that the next whole number below n would be n minus 1, and then n minus 2. Basically, just subtracting 1 from n every time would get you the next whole number all the way down, and then that would take place all the way down to you got to 3 times 2 times 1. Of course, this is only going to work if n starts at a number bigger than 3 times 2 times 1. If n itself is 1, then it's just 1 factorial. Nothing else to worry about. But that's the idea for n factorial. N factorials, you start with n, then you multiply it by n minus 1, and so on, all the way down. And because I know we're going to need this, let's write this down as well. N factorial, once again, is defined to be what you see above, which is n times all of the whole numbers all the way down to 1. But if you were to take and start right there, eliminating the n part, well, now you would have n minus 1 times n minus 2 times blah, 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 all the way down to 3 times 2 times 1. Everything in green there would actually just be n minus 1 factorial, because you'd be starting with n minus 1 and multiplying it all the way down. So technically that could be separated to be n times n minus 1 factorial. And again, this kind of thing does come up, so just understand that that's the case. I could also rewrite it this way if I wanted to. I could say that it's n times n minus 1 times n minus 2 factorial, where it's just the n minus 2 part now that's getting the factorial because the other two terms have already been separated out. Okay, so I think that that is good enough for this specific video. We're going to come back. We're going to talk about what are called recursively defined sequences and summation notation and how to actually apply those to finding sums of certain sequences.